Good morning to people that are signing on. Need to get started now that it's 8:05. So we're still working on section 3.5, and we'll be finishing that up tomorrow in the notes. We've got a little bit of word problem stuff that we have to wait for tomorrow for. So we've already reviewed solving exponential equations, algebraic, graphically. Today, I'm going to spend a lot of time on review solving logarithmic equations, algebraically and graphically, and then applying Newton's law of cooling and these extension topics. We're not necessarily going to be covering everything that was in the packet if you did print out the packet or if you have the packet, but tomorrow the notes will be about the word problem parts of that, and then I probably will try to get a little piece of 3.6 in just to make sure that we have enough time next week to finish it up in 2 days and have a day of review before we take the non-calculator portion of the test. So we are back here a ways where we're starting to look at the logarithmic piece of this, so the inverse of those unknown exponents that we have. And method A says condense to a single logarithm, because once we do that, we can use exponentiation, which is the snail shell method, to figure out what we need for an answer. So you isolate the logarithm piece by condensing it, and then convert it to exponential form or exponentiate both sides. And this again, the non-fancy way of saying exponential form would be by snail shelling. We'll do that. And then, like it says, solve and check. Because with logarithms, we can get extraneous solutions. And we're going to look at that immediately and then talk about that as we go through these problems. Method B, get one logarithm on each side. So if you do have multiple logarithms and they're actually on both sides of the equals, then we need to figure out, are they the same logarithm? Because if they are, then they don't matter anymore. They're equal. Just like our bases being the same before made it so that we could drop the bases out of the algebra. Same thing here. And use those one-to-one properties and solve and check. So, example 2. Solve the logarithmic equation algebraically. And using method A would be putting this in exponential form. So the first thing you do is you check to see, is the logarithm isolated on one side? And it is. There's nothing but logarithm base 3 of the quantity x plus 2 on the left-hand side. So by exponentiating, which is snail shelling here, we'll have 3 to the 4th equals x plus 2. 3 to the 4th is 81. And then we'd subtract 2 from both sides. Now to check it, and I'm not going to necessarily check every single problem today, but to check it, we certainly could just take the 79, substitute it back up in the original, and 79 plus 2 is 81, and snail shell it in our head and say, well, is 3 to the 4th 81? Yes, it is. I've got it. Now, the other method is to say, okay, let's just purely follow the language, the vocabulary, and exponentiate both sides. Now, this is the one that feels a little awkward, and that's because once the logarithm is isolated, what we need to do is think, okay, exponentiate both sides means I have to raise something to a power. And exponentiating both sides means we have to raise both sides to the same power, which would be this time the opposite of what we would normally think of, and that's giving it a base of 3. And that's because here, 3 to the logarithm base 3, those are inverses of each other, and that's just going to cancel out. So this will become x plus 2 equals 3 to the 4th. And we get the exact same answer. So whether or not you're snail shelling or you're actually physically putting a base on there to raise it to that logarithm base 3 of x plus 2 power and to the 4th power, this gives us the same answer. But that's not always the case, and that's why we're looking at a couple of examples before we get started here. So with b, exponential form for this one, we would have to remember that common logarithm, which is the logarithm that doesn't have a base listed for us, has a base of 10. Then we would snail shell. So 10 squared equals x squared. 10 squared is 100. And then, of course, we'd take the square root of both sides and get positive and negative 10. Now, that should worry us because when we raise something to a power and our bases have always been greater than 1, it should come out positive, right? But when you put the negative 10 back in for x squared, you see, oh, that's how they're going to take care of it. Because negative 10 squared would be positive 100. And then it'll make perfect sense. Now, if we use the properties of logarithms to expand this and then solve it, here's what happens. That 2 that we see for an exponent in logarithm language is going to be multiplication, so we have to bring that out in front. And then I don't know about you, but I'd say that logarithm is definitely not by itself now, so I would divide both sides by 2. And then we would snail shell or exponentiate, so we could raise this as a power for our base of 10, and these two would cancel out, and we would get x equals 10 to the first, which is just 10. However, we lost a solution by doing it that way. We already know from exponential form by snail shelling that we're supposed to get two answers, that it's supposed to be a positive and negative 10. But with the second method, where we expanded first and then solved it, we only received one solution. So what we want to do is take a look at this and see what's really going on. So I already put in the logarithm of x squared and a 2, because we need to see where those are going to intersect. So if I hit zoom 6, this is what I see. And then I remember my solutions were at negative 10 and positive 10. So I'm going to change my window so I can get a little better look at those solutions, make it a little bigger. And it does have two solutions. Our y equals 2 is hitting that graph in two spots. And we're not going to be shocked to see that those two spots are at negative 10 and positive 10. So, expanding probably isn't the best way to go. I mean, as we look at our directions up here, we see that it says, hey, condense, then do your exponential. And that's the way that we need to be thinking as we work through these problems. But even more so than that is a little bit deeper, and that would be, I suppose we better put a sketch on here, huh? So that your notes are looking complete. Are your answers the same? No. So when our answers don't come out the same, what really happened? Well, we lost an x value, and that x value is from the domain. So I go back and think, is that something I should have known about? And the answer is yes. As I look at the problem, I see that it had x squared. That's a quadratic. Quadratics are degree 2 polynomials, which means we should expect two solutions. And we did get two solutions. But over here, when we expanded and we took that 2 away from the power and used it as multiplication instead, we were losing one of those. So domain-wise, the domain for x squared, well, that's everything as far as logarithms go. We could put in positives or negatives and we'll be just fine. But the domain for x when we're working with logarithms is from 0 to infinity. So we lose those extra x's. And that's why it's important for us to kind of think before we start the problem. Do we have an x to the first? Do we have an x squared, an x to the third? You know, what should we really be looking for here? And the true answer is, of course, both a positive and a negative 2. So having two solutions. And I'm going to write here in case somebody looks at the notes later. That'll make more sense, that we talked about that as a quadratic, which is a degree 2 polynomial. And checking is a really good idea with logarithms because we do get extraneous solutions. Whenever we're starting to change powers on something, there's always that possibility. So example 2 says, let's use that method A. So solve the logarithmic equation algebraically. And method A was all about condensing, doing whatever we have to do to get a logarithm by itself on one side, and then exponentiating. So we'll subtract 4 from both sides. And then we'll divide both sides by 3. Because again, the goal was to have this say logarithm of something. So we've eliminated everything else that was on the left-hand side of that equation. Now it's ready to exponentiate or snail shell. So it'll be 3 to the 4th equals 2x. And 3 to the 4th is 81. And we'll divide both sides by 2. Again, you can check it by hand by taking 81 halves and putting it back up here and thinking 81 halves times 2, that's going to be 81. Snail shell this in your head. 3 to the something is 81, and then you can multiply your answer because 3 to the 4th is 81. 3 times 4 is 12. 12 plus 4 is 16, and it works. You could also use the left side as y sub 1. And the right side is y sub 2 in your graphing calculator, and make sure that they hit each other at 81 halves. So totally checkable. Now thinking about method A, condensing and snail shelling. I'm looking at D, and I'm thinking, okay, I'm going to have a problem this time, because both of these are linear. The problem we just did was linear, so one solution makes total sense. But to condense that one, addition in logarithm language means multiplication. And when I do that multiplication, I'm going to be creating a quadratic. Now, to condense it, there was nothing else I could do. I mean, that's what I had to do in order to condense. That quadratic has to be there. So I'm just going to continue going and realize that while I may find two solutions, this really should only have one. So we'll probably see an extraneous in the end, but let's see how it works out. Again, the base of common logarithm is a 10 because we have a base 10 number system. Snail shell, 10 to the first equals x squared plus x minus 2. Then we'd go ahead and subtract the 10 from both sides. So 0 equals x squared plus x minus 12. And now we're going to factor, because that's our first and best way to solve quadratics. And this one's not too tough. We've got x plus 4 and x minus 3. So we have two solutions here. X equals negative 4 and x equals 3. But again, in the back of my mind, I'm thinking, really, there was only supposed to be one. Now, this one is pretty obvious. Negative 4 is going to be out, because as soon as you think about taking that negative 4 and placing it back into these parentheses, you realize negative 4 plus 2 is going to be negative 2. And negative 4 minus 1 is going to be negative 5. And you can't raise 10 to some power and magically make it negative. It's not going to happen. So this was extraneous, not a solution. That's an undefined solution, which we just call extraneous. So whether or not, like I said, you check your answers with algebra, you check your answers with the graphing calculator, one way or another, you need to think through this and say, okay, this is why this is working, this is why it's not working, and go through it that way. E. That has a lot going on, a lot more than what we just had in the other problems. But again, the method is, hey, let's condense it and exponentiate. Well, x to the first, expecting one answer. But I see that this has multiplication out in front for both of these, which means I have to put those powers back up in order to condense. Now, one other thing I'm checking while I'm writing it down is, you have to have the same base. We can't do this problem this way unless both of our logarithms have the same base, and they do, so we'll be able to put those together. And what we would do now is say, all right, I've changed the powers. I know that. I can see that. I'm probably going to have to worry about extraneous solutions when I get done. But subtraction in logarithm language is division. Looks like so. Hey, wait a second. We could cancel two of those out because we have the same exact binomial on the top and the bottom. We'll get logarithm base 4 of 1 over x minus 5 equals 1. All right, well, that's not so bad. So then we have the logarithm isolated on one side. We can go ahead and snail shell and see what we get. So 4 to the first equals 1 over x minus 5. And then we could go ahead and say, you know what, I'm going to throw a 1 underneath here, and I'm going to cross multiply. So 4 times the quantity x minus 5 equals 1. 4x minus 20. Oh, I better take it up here. I'm not going to have enough room. So 4x minus 20 equals 1. Add 20 to both sides and divide by 4. Well, I was only supposed to get one solution, so even though powers were developing as I went through this, because they canceled out, it did stay linear with our x to the first, and we have 21/4. Again, quick check it algebraically. 21/4 minus 5. Well, 21/4 minus 20/4 would be 1/4. And 4th base, 1/4 power, 4 to the something is 1/4, and you just go ahead and kind of do those in your head to see what you get, because this would be -1, and then we'd have the same type of thinking here, where we have our 21/4 minus 5 is 1/4, 4 to the -1, so 2 times -1 minus 3 times -1 equals 1, and it does. So again, you could check with the graphing calculator, totally up to you. Usually if you just think about that domain and how many solutions you're supposed to get as you work through a problem, you're going to be fine. Method B. All right, so going back to method B, and I don't want to scroll to it, so I'm going to read it off again. Get one logarithm on each side and use the one-to-one properties. Solve and check. All right, so we still need to condense, which means with addition here, that means multiplication. And I'm already thinking, hey, both of those are linear, so I'm probably going to have something extraneous because I have to multiply those two together. Well, that's okay. We'll just think about it when we get to the end and double check our answers. So natural log of 3x squared minus 3x minus 2x would be minus 5x plus 2. And on the other side, I'm thinking, well, if I'm supposed to condense, that 2 has to go back up as a power, because multiplication becomes an exponent. Oh, look at that. They both have natural log. Well, of course they do, and that's because this was for method B. So they both have natural log. And we realize, well, we don't need that anymore. We need 3x squared minus 5x plus 2 to absolutely equal x squared. That's the only way this is going to work. All right, well, that's a quadratic. So again, thinking all the way through the problem, probably going to get two solutions. One of them is going to be extraneous. Let's subtract x squared. And we'll hope for the best as far as factoring goes. We don't have a greatest common monomial factor. There are no special patterns here, but the good news is the only choices for the first times first would be 2x and x. So if we just get creative about where we put these numbers, we should be fine. And we need two numbers that multiply to positive 2, but somehow add to a negative, so they would both have to be negative. So here, if outside times outside is negative 4x, and inside times inside is negative 1x, we'll get that negative 5x that we need. And last times last is positive 2. So our two solutions come from these two factors using the zero product property. We'd add 1 and divide by 2. And then the second one over here is going to be x equals 2. And at first you think, well, this does have two solutions. Hey, good job, got them. But you have to remember, when we started, it was x to the first. So let's take a peek. If we put 1/2 in this first set of parentheses, 3 times 1/2 would be 3/2, and 3/2 minus 2, wait a second, that's going to be negative. And you can't raise e to some power and get a negative number. So x equals 1/2 is extraneous. And then you just run through, well, is 2 going to work? Oh, this would be positive and this would be positive. And this one, you could check with your graphing calculator because we have a natural log button. You could just punch it in. Natural log of 4 plus natural log of 1, does that equal to natural log of 2? But they did want us to take a look at the graph on the graphing calculator as well. So let me put that up here. Turn off the ones that I have used previously. Pretty obvious. These two graphs are only going to hit each other at one spot. And again, you could go to the table feature with this one, or second trace, number 5. Now this is something interesting that happens when you try to use intersect with logarithms that I wanted to show you. Notice it says first curve, but it hasn't picked a line yet. We're not used to that, or it hasn't picked a curve yet. And that's because with logarithms, remember our domain is restricted. So we're going to have to hit an arrow or a couple of arrows, usually the up arrow. We'll get that to actually grab onto one of those two graphs and enter, and then get it to go to the other graph. Pop it up. By using a little creative arrow work, we can get there. And we can see that the intersection is, in fact, x equals 2. So, if you have time when we get to the graphing calculator portion of the test, it is a really good idea whether or not you check them just by plugging it in algebraically, or if you check it with your graphing calculator. And always remember, the graphing calculator does have logarithm base 10, common logarithm, and logarithm base e, natural logarithm. So let's see, looked kind of like that. And kind of like gotta figure out how to get this blue marker fixed on this smartboard. something goofy going on with that. All right, so checking it, always a good idea when we're talking about logarithms, but especially when we know how many solutions we're supposed to have, and we know that we're not getting that we have too many. Now, this says solve the logarithmic equation algebraically, and again, we're supposed to use method B. So with this one, taking a peek, and this one is a quadratic. So it's possible we could get two real answers out of this. So we want to think about that as we're working through. And the first thing we do is we condense, which means we have to put that left side together. Addition is multiplication. And again, that makes me realize, well, I'm up in the power here, so I might have some extraneous solutions. And you just keep that in mind as you're working through it. So next up would be, hey, they're both logarithm based too. I don't need that. Or if you wanted to exponentiate, you could do that. You could put a 2 here. You're going to see, hey, this is going to drop out because those are inverses. But here's the incredibly important step with this problem. We can't just divide by 3 and take the cubed root because we're only going to get one answer. And we know that we should have 2 since this is a quadratic. So we're going to have to move everything over to one side and factor in order to see all of the solutions. This one does have a greatest common monomial factor. You can take a 3 out of both of these. Oh, excellent. That's a difference of 2 cubes. And my Algebra 2 students are learning that difference of 2 cubes pattern and formula right now. So the formula for difference of 2 cubes. For me, math is not about memorizing. It's about thinking logically about what's going to happen. So when I look at a cubed minus b cubed, I think, well, if it's to the third power, there has to be at least one factor of a minus b in there, for goodness sake. And then I just think backwards about what I would have to multiply that by to get to a cubed minus b cubed. Pretty obviously, a is going to have to be multiplied by a squared in order to get a cubed. Pretty obviously, negative b is going to have to be multiplied by a b squared in order to get b cubed in the back. But here's the problem with that. If I multiply that right now, I'm going to have a middle term. So how do you get rid of the middle term? Well, you make sure your middle term in the second set of parentheses is the opposite of what you have in the first set of parentheses. So your middle term would have to be a plus ab to make that happen. So that's our formula for the sum of 2 cubes. All we have to do is figure out that this is x cubed, and this is 2 cubed, and substitute x and 2 into that formula, and then we can keep going and find our solutions. And we get one really nice one here right away. But again, thinking about the fact that this was quadratic when we started means we can't just say, hey, I don't care about those other 2 solutions that I have over here. So I have to figure out how to get solutions out of x squared plus 2x plus 4. Well, what we would have to do is say, hey, is that factorable? Maybe that's a perfect square trinomial. Well, this is x squared, this is 2 squared, but 2 times x doubled is 4x, so that's not going to work. So we'd have to complete the square. We'd take our b, divide it by 2, and square it. And then we'd square root both sides. and simplify. I guess I'd take care of it right now. Simplify the square root of negative 3 and make it I square roots of 3, and then subtract 1 from both sides. But if we take those two imaginary answers and we put them in this first position where x is right here, negative 1 minus the square root of negative 3, negative 1 plus the square root of negative 3, either way, we don't care about those imaginary solutions, and they're not going to work because it's going to come out to be negative, and you can't raise 2 to a power and get something imaginary or something negative. So these are not working. Which means even though this was a quadratic, it only had one real solution for us to find, which was that x equals 2. Now that doesn't mean that at this point you say, well, Cedarholm, then I could have just divided by 3 and taken the cube root, because it doesn't work that way in most problems. We always have to try to factor and see if we can find them all and show all of that work. So again, you could graph this, left-hand side. You'd have to use the change of base formula. It would really be a monster if you punched it into your calculator. You'd have to do log of x divided by log of 2, and all of that in parentheses, plus log of 3x squared divided by log of 2, all of that in parentheses, and then make your y sub 2 equal to log of 24 divided by log of 2. And you'd see they only intersect at 2. H. You know it's going to be good when it says extension. That means a little bit above what we're going to ask you to be doing in the homework and on the test. Hint for this one is use the change of base formula. So I see I have logarithm base 100 of x squared. What are they doing? So that's why they gave us the hint, because we could rewrite this as log of x squared over log of 100. Now, this is important. We know what that number is. That's the reason they wanted us to write this with the change of base formula, so we could see, hey, wait a second, I know what that is, because this is base 10. 10 to the second power will give me 100. So now what should I do with that? Well, I need to make that 1/2 logarithm of x squared, because we're supposed to condense that left-hand side. So I have to use that 1/2 that's being multiplied as an exponent. So this gets me thinking again. Here we have a quadratic, here we have a cubic. Possible that we could get 3 answers for this problem, so we need to keep an eye out for that. All right, so the 1/2 goes back up and gets multiplied by the 2, and we get the logarithm of x to the first minus the logarithm of x cubed equals 6. And now we have subtraction, which is division in logarithm language. And we realize we can simplify that. And then we'll need to snail shell or exponentiate. So we remember it's base 10. And then just like before, I would put 10 6 over 1. Most people like to solve proportions nice and easy by cross multiplying. Divide both sides by 10 to the 6. Now there's a reason I'm not writing out what 10 to the 6 is, and that reason is this next step, because we're going to take the square root of both sides. And x will equal plus or minus. The square root of 1 is 1. The square root of 10 to the 6 would be 10 to the 6 to the 1/2 power. So that's going to be 10 to the 3rd. And now I'll finish up my answer by figuring out that 10 to the 3rd is 1/1000th. I should put this in a different color for people that look at this later. So we have positive and negative 1/1000th. And I go back to thinking, well, we were supposed to get 2, 3 answers here. Positive 1/1000th and negative 1/1000th will work here. That's probably in the glare, isn't it? But not here, because if we put that negative 1/1000th in this position and raise it to the third power, it's going to be negative. And you can't raise 10 to some power and get a negative out of it. So the only solution to this one is positive. Again, it actually wouldn't be quite as hard to graph this one, to put it in your graphing calculator as the last one, and that's because this is base 10. So you could always check it. You could use the change of base formula on this first one and plug in log of x squared divided by log of 100 in parentheses, and then minus log of x cubed, make that y sub 1, and then put in 6 as y sub 2, and see that there's only one solution there, one spot where they're going to hit each other. Now, the last couple of days, I've been looking at this and thinking, maybe I'll start the word problems. And I don't think I'm going to do that because I do want you to have the feeling like you've covered one big topic today, and it was one big topic. We went through a lot of stuff about logarithms. So tomorrow's video will cover the rest of the word problems from day 3 here. And then I'll probably just get a little teeny start on 3-6, like maybe the first page and a half of the notes for that. But for today, just move that stuff down, because I know that glare is up there. Page 301. 7 through 10, 17 to 18, 25 to 28, and 35 to 38. So you start to feel a little bit better about, more involved logarithm problems before we continue on with the word problem pieces here. Always welcome to stay on and get started on the homework, ask questions if you need to. Also welcome to, sign off, and if you can get to something in the next, I guess we've got about 12 minutes left or so, you could always pop back on and ask about it if you want to. So have a great day.